Good morning, everyone. My name is Daniel, this is Saint, and today we're going to be giving everyone a quick rundown onto the topic of particle image velocimetry, which is PIV for short. So, as a quick introduction or table of contents to what of the specifics of what we discussed today in our conversation, after a brief discussion on the topic of how we can experimentally measure fluid properties, especially fluid velocity, we can then dive into the what particle image velocimetry is, its key aspects of how PIV is run, before finally getting into some numbers and a short discussion as to how it can best be utilized. So, as a brief introduction, one of the questions that many graduate scientists need to figure out when experimenting with fluids is how we can diagnose the fluid properties of an experiment without drastically affecting the fluid. To be more specific, how can we quantitatively obtain data about flow velocity in different kinds of experiments? At an undergraduate level, flow is typically simplified as a constant over a period of time, or only relevant for initial and final conditions. As we investigate further into the nature of fluid flow in different scenarios, the need for more quantitative or statistical measurements of fluid velocity across a larger control volume and across a larger window of different times becomes necessary to define. An example of what might have been seen as a qualitative data on fluid flow velocity can be seen in my own undergraduate experience is in the measurement of current airspeed with a pitot tube. A pitot tube can be used to calculate the velocity of air by measuring stagnation and static pressure. Having a general understanding of how fast a wind gust is might be good for figuring out if it's a good idea to take your only competition-ready remote-controlled aircraft into the sky, but how can we articulate the velocity of airflow over a larger control volume rather than just at one single point?
So particle image velocimetry, or PIV, is an experimental fluid analysis technique that captures an instantaneous velocity field in 2 or 3 dimensions within the entire plane of the fluid domain, which effectively looks at the volume of complex fluid flows such as turbulent, unsteady flows and vortex flows, where it's difficult to look at with conventional analysis techniques. However, there are always limitations using experimental techniques, such as the required laser intensity for light scattering, tools blocking the cameras, other techniques being more optimal for higher velocities such as anemometers, and the cost of equipment, where commercial PIVs would cost around $2,000 and professional equipment would be around $100,000. Here's an example video of analysis of fluid flow around an internal combustion valve. See if we can get it working.
Where's the mouse? There's the mouse.
And here you can see the laser shining on the fluid particles as the piston is moving in and out. Yeah. All right, there we go. There's 3 essential components to a successful analysis: the seeding particles within the fluid flow, the light source or laser used to show the particles, and the cameras used to capture the particles at an instance. The seeding of the fluid involves seeding of or tracer particles that are used to simulate fluid properties placed within the fluid. These particles should be effective in following the fluid flow, but also be large enough so that the light shine can be scattered effectively so that the cameras can capture the particles. Some examples include oil droplets, which are typically used for gases where diameters are between 1 to 5 microns, and glass beads or DEHS droplets for liquids. And on the right, it shows some examples of what the particles will look like. And the optimum density, where on the left you can see too little won't be enough to create an effective analysis, but too much would result in image overlap. The light source, typically a laser, is required to shine on particles, where pulsing lasers shine at full force at each pulse, and each pulse is defined as several nanoseconds. The light must be effectively scattered by the particles to be captured by cameras, and since the pulsing laser is quite consistent in pulsing 2 laser sheets can be used to create a time differential for effective analysis. And finally, the cameras necessary for particle images are essential in topographic reconstruction of the fluid field. And these cameras need to effectively follow the laser pulses. So high frequency cameras or CCD charge coupled device cameras are used to follow the fluid flow, as they're light sensitive and quite easy to set up. Other devices such as holographic plates, films, or CMOS cameras can be used for higher resolutions, but are typically only used for slow fluid speeds. And multiple cameras are necessary and are placed at different angles, capturing the particles at a specific point for construction of the velocity field.
So some examples of evaluation and equations necessary to best utilize PIV are described in the slide here. When considering what tracer particles to use in your experiment, making sure that your particle's settling velocity is insignificant when compared to the fluid velocity is key to ensure that the particle will behave as expected during the experiment. Optimizing your laser resonator length is key to maximize the standing waves of light produced from PIV to best obtain strong images for your experiment. When analyzing your image data from your PIV experiment, having a strong understanding of how your optics and camera tools affect the imaged particle diameter is critical to having a higher accuracy of your data-reduced results to what is occurring in reality. An example of how PIV can be used in experiments can be seen in many articles and reports the ASME journal has on fluid mechanics. In this particular case, the PIV is used to obtain flow velocity measurements of a laminar flow separation around a low Reynolds number airfoil. By experimentally articulating the instantaneous flow properties at different points across the control volume across a time frame, how the flow behaves and produces vorticity for a given airfoil at different angles of attack can be consistently measured and used to help design aircraft. One use of PIV used here at Georgia Tech is in the gas mixing study being conducted in Devesh's shock tube and advanced mixing lab. In Quinton's gas tunnel test, where he mixes a high-density fluid over a low-density fluid inside of a wind tunnel, particles are seeded into the flow to observe how the different fluids behave with one another during the experiment, as we can see in the top image. Taking a step beyond simply PIV as a fluid diagnostic, we can see in the bottom photo, Quinton's experiment has also used PLIF, which is planar laser-induced fluorescence, in tandem with PIV to obtain more data for his experiment. When it comes to understanding fluid mechanics experimentally, fluid diagnostics like particle imaging velocimetry is key to quantitatively obtaining data of what reality has to describe for you. That concludes our presentation on PIV. Thanks everyone for listening.
Audience questions.
So how do the particles differ when the fluid is like air or gas versus like a liquid?
So the audience question is, how does a particle differ in a fluid like air or gas when compared to a fluid like water or liquid? I would say like it definitely depends on that settling velocity, which is how the fluid. I'm going to jump back a couple slides through those equations and break this equation down a little bit. How the particle itself interacts with the flow velocity. So in this equation here, which is U infinity, described as, in this case, as settling velocity, we're comparing the diameter of the particle and the density of the particle to the density of the fluid and the viscosity of the fluid. So as long as, well, according to this, my initial assumptions about PIV and my initial studies on PIV and the subject itself, when it comes to that particle, making sure that the particle can be seen or can operate normally and as expected along with the fluid of whatever fluid you're doing in your experiment is key to making sure that whatever particle you're using makes sense for your PIV experiment. Any comments, Saints?
Yeah, I would also say more typically for liquids, they use plastic particles, which where their density is quite similar to that with water, I guess. So that's why they use like these kind of particles for liquids. But for gases, like obviously they'll have to be lighter and travel at faster speeds. So that's why oil droplets are typically used. And these are like really small, like droplets of oil that are used. Yes.
Does smoke or like dust particles work too, or?
I think in an abstract sense, if we're just doing like pretty unprofessional, like understanding, like hypothetically speaking, these type of particles can be used, but it's probably not optimal to use in an experiment, right? So you want to rely on something that's a little more consistent and like can be repeatedly reproduced, like a manufactured or a set defined particle versus like something like smoke, which can have varying densities, or like dust, or like sand, for example, which can have like varying densities. Like when it comes to like, for example, the grains of sand on a beach, each grain of sand might be different, right? So when it comes to that sort of, from that perspective, probably something more finite and more easily repeatable for an experiment would be more efficient in your experiments. Thank you for your question.
They would have those particles, they're all, what's the term I'm looking for? They don't depend on orientation, right? They're all like spheres or that sort of thing.
Yeah, the question was, making sure that, the particles are typically all spherical and not have like different orientations. Yeah, typically in PIV experiments, these particles would be like round. And when we really get down to like high magnification experiments, because the nature of PIV, we're recording a video at a varying like frames per second of these fluids or of these particles moving through the fluid during the experiment. When we look at that at a high magnification, like we typically generalize them as like circular particles. Yeah.
I know that's not the fluid mechanics part, but I didn't understand what you're talking about for the lasers here.
Generally speaking, with my fairly elementary understanding of lasers, when it comes to how lasers how the particles absorb and like reflect the laser intensity light at different like wavelengths and different intensities, when it comes to when it comes to light waves, there are standing waves at higher amplitudes and lower amplitudes, and when we're talking about particles with like very small diameters, like microscopic levels of diameters, to like reflecting back into like an optical camera, making sure that our wavelength and our spacing in our refraction and our optics is appropriate to make sure that our camera best absorbs the light reflected from those particles is, this is just one equation to many equations that goes into the consideration of diagnosing or fluid diagnostics.
Are you doing 3D PIV or just
For these equations, it's 1D for these equations that I've kind of utilized from the textbooks and the papers that I've read. It typically assumes that the particles are 1D. When it comes to 2D and 3D systems, it can get rather complex, but I'm sure that with a couple extra setups and cameras and lenses at different angles, we can best understand how the flow works in 2D and 3D situations.
And the last slide, maybe just explain what are we seeing of those two different things?
So
I know that's not, you said that's Quentin, I don't know who that is.
He's a PhD student in my lab at the Shock Tube Advanced Mixing Lab over at Georgia Tech, which is here.
What is
yeah, to kind of briefly cover what's going on in the first photo. The first photo is a photo of a frame of PIV, which we can see the different particles in the mixing of different fluids. Generally in his Quentin's experiment, which he's doing his PhD on, he is mixing he's got a gas tunnel or a wind tunnel with two different levels. The upper level being a higher density fluid, the lower level being a lower density fluid. And after like removing a slide or activating some sort of mechanism, the higher density fluid is driven into the lower density fluid via gravity and produces a mixing within that wind tunnel. So what is going on in this above image is a photo of PIV in action, which we can see the different particles of the fluids and better visualize what is going on with the mixing of the two fluids through those particles. And across an entire experiment, we would have multiple photos of this at like as what he told me, about 2 or 3 frames per second. And from that, we can articulate the velocity. A camera or a program or go and analyze each and every particle and articulate the velocity field. The bottom image is the same instance of photo, or the same time step, or same instance of time of the experiment using PLIF, which is another diagnostic, which wasn't discussed in length today in our discussion of PIV, but it is another diagnostic, PLIF, which is planar laser-induced fluorescence, which is seeding a fluid with a certain substance that fluoresces under a induced induced wavelength of laser. It's another presentation or two to discuss what is going on PLIF, but I think it's really cool to kind of see how PIV can be used in tandem with PLIF to produce more data on the same experiment, both being pretty non-intrusive ways to measure the flow properties of an experiment.
Any other questions from the audience?
Just to make sure I understand the picture, the darker areas are the less dense fluid that that were permeated?
I want to say, the darker areas in the top photo.
By darker, I mean less particle.
I think it's more of a situation with the laser and how the light or the laser being used is reflected in that area. It's not necessarily that there is no fluid going on up there, or it's just that when we're talking about, PIV, which is particle imaging velocimetry, we have a high-powered laser to reflect off of the particles at a certain area, and when it comes to that sort of precision, when it comes to, for example, position, right? These particles in the center is more in focus, or more reflecting more light back into the lens of the optics in the center. But although there are particles and there are fluid in the above and below sections, the laser doesn't reflect those light particles back into the camera in those scenarios. Yeah. Thanks everyone for your questions, and thanks everyone for listening to our presentation. I gotta get out. Yeah.
Shouldn't be a small bit.
So those presentations, please, after you're done, if you can, I made a link on Gradescope to upload the PDF. So upload the PDF, and if you work in a group, maybe just a brief, put a few sentences about what you did in the group. Each person say something. Just so I make sure I try to make sure there's no freeloaders.
And you want that all in that single PDF? Upload to that Gradescope? Yeah. And we each individually upload the same PDF?
Yeah, but a different statement. Yeah. Yeah, and there's just no deadline on that. Who's up next week? Okay, good. And this is the T. Okay, all right, good. We'll have the quiz, be having the quiz next Wednesday, so maybe you want to present Monday, or we could have it before the quiz too. We can have it before the quiz. It's not going to take, quiz is not that long. But you can let me know your preference if you want to do it Monday or Wednesday next week. Presentation, we have a quiz on Wednesday. So you can let me know if you want to get present on Monday or Wednesday. Either way is fine. You can think about it.
Maybe Monday.
Maybe Monday? Okay. Okay, so the grader had a take-home test on Tuesday, so the grader's not done. But so we don't have delays, I posted the current grades, which is only half the problem set, and some of them he didn't get to yet. So if you have a 0, it's probably because we didn't get to it. But I did want you to see it because, and I've also posted a solution set. So we will have the quiz next Wednesday. I think you should try to. Okay, so let's see. It's out of 13. We have 1, 2, 3, 4, 5, 6, like 6 13s, so 6 perfects so far, and then like I would say 6 or 7 12s, which are fine. 11s and 10s I think are fine. But I would say if you got between if you got basically, so it's out of, if you got like less than 30% on this homework, it means that you probably need to start working in a group. I don't penalize you for working in a group. In fact, this class is difficult enough that if you're unfamiliar with the material, you really want to try to work in a group. So on Mondays and Wednesdays, for example, Don and like 3 other people are sitting there eating lunch and hanging out. So feel free to come by and at least say hi. If your groups get too big, maybe you have to just like share contact info. But basically, if you got less than the 30%, you probably need to email. So maybe I'll just say email and meet me. We're gonna have there'll be an online office hours. It's gonna be Monday at 4:30. Usually it's Monday, Wednesday at 4:30, but I can't do it on this. I can't do it. So no online office hours today. And then we can also make it office hours by appointment. Usually they're after class. But this is introduction to fluid mechanics. So unfortunately we already had some people drop the class before I even got a chance to tell them to try to stay. But try to stay with the class. I'll be teaching this class again next year. So if you drop it, you're going to see me again next year. Next year, there's no escape. Just you got to work in a group because you should just be getting a few points off. But if you're getting like less than 30%, it means that if we do index notation for any of the future homeworks, and sometimes we do, you'll have some trouble. And also, that quiz is going to be very, very difficult for you if you're having trouble with all the time. So email and meet me, I want to make some time. So next week. So you have all the solutions. Please check them out, and then if there's anything that doesn't that you should be able to reproduce anything on this homework. You should be able to teach someone how to do this homework. So if you have any trouble with it, let's try to make a time and after class, because the class is, as you can see, there are 14 people with 80 or 90% of the homework, so we can't talk about index notation too much during class anymore. But if you're having trouble, you do need to try to catch up. All right. All right. So where were we last time? All right. Before we talked about the homework.
We just wrote down the Navier-Stokes equation.
Yeah.
For incompressible fluids.
So let's just review briefly. All right. So last time. All right. Okay. So we basically had to introduce this. We have this deviatoric stress tensor, and we know it's a function of the rate of strain because the rotation, the omega matrix, has no fluid relative motion. And originally it has 81 different parameters, but we showed because of its symmetric, we could basically reduce those parameters down to just 2. So this is isotropic. That means there's no dependence on direction. So there's no preferred, like, X or Y or Z. And we won't quiz you on this, but basically you can write any isotropic tensor if it's even order as with these 3 constants. And then last time we basically said, okay, well, if it's symmetric, then you reduce those constants down to these 2. And then I said, without much justification, well, instead of calling lambda 1, lambda 2, that's really awkward notation. People like to use mu and k, where mu is your shear viscosity and k is your bulk viscosity. So what I want to start with today is talking a little bit about why, like, does anyone know why they have k minus 2/3? Like, why do we even do this? Why don't we just have lambda 1 equal k? Does anyone know by chance? Yeah?
I think it's a Stokes approximation that we assume k is equal to 2/3 mu.
Possibly. But possibly, I'll show you another example that k comes out. Bulk viscosity. Actually, I've never even. So bulk viscosity. It has to. This is like a viscosity that's not shear. It's like the resistance to bulk, like, expansion. So let's give an example and talk about that. So let's go to the other notes. Sorry. All right. All right. So so we'll start by justifying. So what we're going to do today, we're going to justify the choice of k, and then we're going to derive conservation of energy. Okay. So let's first justify. So our deviatoric stress tensor from last time can be written like this. All right. And remember, we chose lambda 2 is mu, and that's the shear viscosity. Lambda 1. It's not just k, but basically we're subtracting some part of mu. And bulk. So I called it the bulk viscosity, but people also call it the bulk and dilational viscosity. Apparently, if you study acoustics, that's people use that. Because acoustic is all like these perturbations. They just have like small little explosions in pressure. And everything's linearized, apparently. All right. So we're going to consider what we call pure expansion or dilation. So consider u equals x. So I want you to kind of like draw what that looks like, and then write it in Einstein notation, and then basically see if we can substitute that in for Eij. And you can do this. Remember, Eij is equal to, and you can do this with a partner. Remember, Eij is del u plus del u transpose, so we have this plus the transpose. So let's take like two or 3 minutes, talk to someone and see if we can calculate Eij and then eventually tau ij based on this, because you'll need to be able to do something like this for the homework. So first of all, what does it look like? If u is just the position vector, that means at the center you don't have any velocity, right? Here you have some velocity. Here it's a negative position versus negative velocity. Here, same way, and then same on the diagonals, right? And furthermore, as you go further out, you have a higher position, so you're going to have higher velocities. Oops. more exaggerated. So it's like cartoon explosion. What is this in index notation? UI is equal to what? Here, we're going to just write it like this, okay? So see if you can just go forward with that. So go ahead and talk to people if you don't really understand.
That's what I feel like motion. Yeah. I'm with that. That's just 3 lines.
So basically it's delta xi by xi.
So yeah, it becomes
yeah, because he said he was the definition for it.
yeah.
So you're saying that this is
Use that.
so well I assume that so this will basically be delta I and delta I.
Maybe explain that.
Non mais oui,
Say UI X. X.
Are we assuming use symmetric? Are we assuming use symmetric? If use symmetric, the transpose doesn't change. It would just be 2.
maybe one full.
So that's the rows. And this is U2, that's the second row. U3 is the third row.
I don't understand why we don't write it like this, like why do we choose to put I as column and not rows?
Have you seen it elsewhere? That is the opposite. I think it's just arbitrary.
It's just arbitrary.
Yeah, I think that's how people do it.
Okay, okay.
Yeah. And from homework 1, we have a gradient of position vector, don't we?
Like for squares. Yeah, I'm trying to think as well. Like, can the sigma ij, like squared, can that be simplified further?
Sigma ij?
Or delta ij, sorry. Delta ij, like squared, because there are two delta ij components now, right? Or unless I made it. So there's already a delta ij here.
Why
Oh, wait, never mind.
It shouldn't be squared.
It shouldn't be.
Is there any mean to delta ij squared at all?
Well, delta ij times delta ij, we've shown that's delta ii, remember, from the first homework.
Oh, that's right. Oh, this is that would be times, but this isn't times. This is we got that from this, right? So just
Yeah. You just add those. We don't have a times. Where's the times? All right. This is taking a longer than I expected, but we do have some people who got it right. It's actually making me a little bit worried for the next week, for Wednesday. Let's talk a little bit about this. And we didn't we? You did a problem like this in the homework. This a gradient of the position vector, right? All right. Basically, what do you know about position vector here? So, xi is going to be basically, you imagine is, it's saying like if you have u is equal to ux, uy, uz, right? Those three things, and x is x, y, z. It means the velocity is basically just the position, right? We're just saying that, hey, if I want to know velocity, I got to have that position. And what we learned from, let's just go back. What we learned, this is basically del u. This is gradient u. So basically, if you have, this numerator being a position and the bottom, like basically we talked about, you could have dx over dx, you could have dx over dy, dx over dz. These don't give you a contribution. You only get a contribution when basically j and r are equal. So eij should become physically, that's what physically we're doing. We're having all the components, all the different possibilities of j and all the different possibilities of i for that numerator and denominator, right? And so this becomes, because it only becomes something when j and r are equal, we call that delta ij, and we call this other one delta ij. So this just becomes delta ij, right? And eii just, because we're using the same u's and x's, this is delta ii. Okay, what do we find from homework 1, problem 1? What's delta ii? 3. Because
you've got the
basically there's an imaginary summation symbol across all the i's. I equals 1. I is equal to 1 to 3. Right? And then basically that's going to give you 1 plus 1 plus 1, which is 3. All right. Okay, so now we can start simplifying a little bit. So tau ij, we want to use the notation. We said we have this k minus 2/3. Okay. So let's just, the original one was this. Remember, original one was this, and we're going to substitute with the stuff we found. Let's make it a little smaller so everything's on the board. So I'm going to say lambda 1 is k minus 2/3, and then ekk was just 3 times delta ij plus 2 mu delta ij. Now we're just adding these things together, and see this 2/3 is going to cancel this 2. Oh, sorry, 2/3 mu. So these cancel, and then you're just left with 3 k delta ij. Let's expand it again. Okay. All right, now we can start to use and delta ij in the matrix. So this is Einstein notation world. So this is index notation, right? And you should be comfortable going back and forth between index notation and what we call vector notation. So tau, two bars means the nine components. We got 3, k, and then del dot u I. This is the definition of what we did last time. Of where it comes from. So there's no 3. Sorry. Because we had from last time we had tau is equal to k minus 2/3 del dot u times I plus 2 mu e. Okay. Okay. So basically, if you have uniform expansion, your k tells you like just with what resistance that you're going to expand uniformly. All right. All right. So let's talk about conservation of energy. So basically, let's give the word statement. Sorry, I need to state one more thing. And then also del dot u is equal to All right, so what we have, imagine we basically have this velocity going through the surface here. If that thing carries any pressures with it, you might change the energy. We have a normal coming out of the control volume, and we have volume V. So we have to introduce a new variable. Well, 3 actually. And to be honest, we're only going to be using it for this. We're not going to even be do much heat transfer in this class. So energy is a scalar. Internal energy per unit mass, you can consider it to be like the proportion of the temperature of the object or your gas. All right. and Q is your heat flux vector. That's the direction of your heat flux. And we have the notation such that Q dot N is greater than 0, so we have it going. This means such that. Let me just write it out. That looks like a G. All right. Q dot N is greater than 0. So we'll use a similar notation to if you take heat transfer conduction. So when you were in undergrad, we did Fourier's law, which was just kind of one-dimensional. So something coming out of like an infinite plate, infinitely wide plate. So I'm going to use theta for temperature because we've been using T for the stress tensor. And we're going to use stress tensor a lot more than we're going to use temperature in this class. So just like we generalize, we had this idea that the stress could be a function of any of these different components. You could basically have a generalized conductivity tensor that's going to depend on the three-dimensional temperature gradient. Okay, so we've got one term on the left, which is the time rate of change of kinetic energy, and then 3 terms on the right. The rate of work done across the surface by body and surface forces. That's like gravity. That's like a fluid flowing in, bringing in new kinetic energy. And then we've got heat flux, which is different because heat is a transfer of energy. It's not the transfer of matter. So we had to keep those separate. And then you also have any kind of internal heat generation, which is if your thing's on fire or something like that. So let's write all these terms mathematically. The word statement. So we got, and we have to use a material derivative because our control element could be moving and deforming. So what's this first term called? That's a U. One half rho U squared. What do we call that?
The Laplace.
Kinetic energy.
Yeah. Okay, so that's only associated if you have an object moving. If you have no flow, you don't have any kinetic energy. Then we just define this internal energy per unit mass. So to figure out the whole internal energy in the system, you multiply by how much mass you have, which is rho times V. Okay. Now we look at the forces that come from the boundary, from the body forces. Remember, F is usually gravity, but there could be some magnetism or something. So we have this U dot F in general. Then we have the surface forces, which Cauchy originally wrote as a T vector, which depends on the orientation of the surface. And then they said, hey, we have all these divergence theorems. Having a T vector is not that useful. Let's take that information, the T vector, because we know there's 3 directions of T depend on 3 directions of N. So let's just write that as 9 components of this basically stress tensor. And also so we can use divergence theorem, N dot T. So they put all the information in the stress vector into this tensor. And then we have the heat flux across the surface. Again, this is surface integral, and the heat generation, which are independent. All right. So this is the math form of what we just wrote, accounting for all the different mechanical and thermal energies. So what we're going to do is we're going to separate this into 2 separate equations. One's called the mechanical energy equation, which is if you don't have any heating elements, what we're going to use. And one's a thermal energy equation. And we're going to do that by looking at the Cauchy momentum tensor and integrating that dotting with velocity, integrating that to get the mechanical energy equation. We're going to subtract it from this thing. So this is not super useful for you right now because you have surface area, surface integrals, and volume integrals. So we have to do the same trick as last time to basically make them all into a differential form by making the surface into volume integrals. So we're going to apply divergence theorem. All right, u dot f is going to go right here. This n dot t dot u, we saw that before. That's going to become divergence of t dot u. Yeah?
Row over there on the left hand side, like you have it outside and then you have another row with the U.
Yeah, I messed up. Thank you. No, I messed the inside.
Right here.
It should stay. It should go. Thank you. All right. Same with del dot q. We use a divergence theorem, and then plus rho q h dv. All right. So basically, I'm not going to mess it up, but you see there are two terms that became divergence. Those are clearly from the divergence theorem. Okay. Question?
Did you use to get the material derivative inside the integral? That's not part of divergence theorem. Is that transport theorem, or is that on the left side?
Yeah. All right. Using LTT. All right. Okay. So all we're doing is, because the volume is arbitrary, we're basically going to, the volume is arbitrary, we're going to just, that means the only way this can be true is if the integrands are all equal. Only comment I have is that this negative sign for del dot q is just because we call heat flux outward to be positive. That's just a sign convention for q. All right. This needs to be simplified. I'll leave it to you as a, so if you remember, there's some identity. That identity dealt with two vectors, but you can show with index notation that you can apply it when one of them is a tensor. And if you are not comfortable with it, maybe this is something you can practice before the quiz. Okay. But basically we have the divergence of the first part, and the divergence of the second, and the gradient, double dotted with the gradient of the second part. Okay, so altogether we have, this is the one we're going to box. And since Cedric bought this use of the Reynolds transport theorem, if you wanna show that on a separate piece, you're gonna have some extra credit that works. All right, so we have exactly what we have above, except now we have 2 extra terms. Let's box this. So the problem with this equation is it has all the terms together, mechanical and thermal, but actually those parts are independent. So let's do a separate derivation that's much, much shorter for the mechanical energy equation. So So let's start with the mechanical energy equation. Okay. This is what we derived by looking at the, remember this is the inertia, MA basically, and then we had the surface stresses, which is originally integral of T, little t, across the surface, which by divergence theorem across the volume, that becomes divergence of the stress tensor and any body forces. So this equation above has units of force per volume, right? And we want to turn that into energy. Well, at least energy per unit volume, you're going to be multiplying by velocity. Because to review, remember, force times velocity is going to equal to power, right? So that's the rationale for what we're doing. And we're going to use this idea that this can be written as, because the density for incompressible fluid doesn't depend on time or space, we can write this like this. Where when I have something like u squared, it's equal to u dot u. Similarly, if you remember, we had del squared was del dot del. Okay. All right, so together, we now have the mechanical engineering equation.
Where did the 1 half come from?
It comes from the chain rule, because if you take the time derivative of if you take basically you have some function of the squared, the 2 comes down. Yeah. Okay, so this is the mechanical energy equation. So let's interpret this together. The right-hand side is the time rate of change of the kinetic energy. Basically, if your control volume is just all those particles are decreasing in speed, right? There's no elastic forces in fluid unless we're doing non-Newtonian stuff. This is work done by surface forces. Remember, T has two components. A pressure that's along the diagonal, which is only acting normally. So you basically, if you have a piston, U dot P is going to give you your basically expansion, contraction type changes in energy. And then you have work done by body forces. If your whole thing is rising or falling in a gravitational field. For example, if F equals rho g, then this term is, then U dot F is basically the time rate of change of your gravitational potential energy. All right, so we'll call this double star. So this tracks all the types of energy from mechanical energy, from basically movement. Any kind of, if you don't have a velocity, you don't have any work done, okay? And then if we subtract that energy, that equation from star, we get the thermal energy equation. No, sorry, no vector. And for the quiz, for the homework, where you're doing the bathtub problem, actually we'll have to derive. We're going to separate T double dot del U into one more thing. We'll be using what comes out of all this. So this is okay. So this is a thermal. Okay, this is the thermal energy equation. Yes. Yeah.
So before you took out the row, but then there's another row. So what happened? Is there a row?
I thought I fixed that, but I guess I'm messing it up everywhere.
You fixed it up top, but you didn't carry the fix.
Hold on. Okay. Yeah, because it's this is incompressible, so rho is not a function of time, so I'm pulling it out. Yeah, it should be just 1/2 u squared in those places, and this one seems fine. Okay, thanks. So this is time rate of change of this time of internal energy. So whether it's getting hotter or colder, internal energy. This is the heat flux. Remember, it was a surface integral, and then we changed it to basically divergence so we can make it a volume. And this is a heat generation. All right. Now, how do we interpret this stress tensor double dotted with the gradient of the velocity gradient? This is going to be a combination of two terms. This is called viscous dissipation plus what we call dilational work. Okay, there are two ways. There are two kinds of information in del U. For the example we did with u being the position vector, that was pure dilational work. There was no shear. There's basically no velocities that are different from there's no kind of like tangential motion. Let's do a little bit of, let's explain this a little bit, how we get those two types of work. So we spent a lot of time writing the stress tensor into the hydrostatic component and the component that depends on fluid motion. All right, let's substitute these in here. T double dotted del U. It's going to be negative P I double dotted del U plus tau double dotted del U. All right. All right, this is a good index notation exercise. So this simplifies. We don't have a tremendous amount of time, so I'm just going to probably tell you. So this is phi equal to viscous dissipation. We end at 10:45, right? Okay, then I'm just going to, okay, so the I matrix has got 9 components. We can write that as delta ij, okay? Del, and it's going to have these, if you double dot it with del u, I'm just going to tell you right now, you should practice this at home, that basically the two unit vectors from I are going to dot it with the del u vectors, and then duj dxi, which you can write as duj dxj. Oops. And that is del dot u. Okay. So putting that together, we have t double dot del u. Our new interpretation is that we have two terms. One that goes as the divergence of velocity, and the other one is what we called phi. I told people I'd try to use capital P because this is pressure, but that's pressure, not density. This is dilational work. Really, so clearly, because for Navier-Stokes, for Newtonian fluids, we do not have any divergence of velocity. So this is only if you have like a gas or something like that. And physically, it corresponds to PV work. In thermo. So we have an incompressible Newtonian fluid, which is what your bathtub problem is on the homework. water is Newtonian, so del dot U 0. And then the version of, so that means the deviatoric stress is just going to be this 2 mu times E. So for Newtonian fluid, dilational work vanishes. And we're going to write this dissipation phi as 2 mu E double dotted with E. Okay. And this should be greater than or equal to 0. This is the dissipation for an incompressible fluid. Okay. This is not a bad place to transition to talking about, for very briefly, how you're going to use this on the homework. So, for example, number 5 in the homework says, how long would it take to heat your bath water from room temperature to boiling by stirring with your hand? So what I would suggest is you so this is number homework 2, number 5. So you'll be using this thermal energy equation. All right. Okay, and you're going to assume that basically your bathtub's like, yeah, it's just pretty. I mean, to be honest, that's not a good assumption because you're going to find out this is going to take a long time to do this. But I don't really want to calculate stuff about bathtubs. And you are generating heat, but it's through viscous dissipation. It's not through basically like chemical energy to internal energy. So these, you're going to show that these are both 0 with some assumptions. And then phi, we have this E double dotted with E, but remember that E scales as basically this divergence, sorry, not divergence, gradient of U, right? So you can write phi as mu gradient of U squared. And then I would just make a very, very simple velocity distribution, like some kind of linear velocity distribution. So if you have a bathtub that looks like this, and you stir with your hand, well, we'll talk about boundary conditions starting next time, but all of you remember there's a no-slip boundary condition on the bottom. So you have something like this. I would just keep it 2-dimensional because this is we just want to have a basic idea. So you basically have this velocity distribution here. So get some idea for basically what your velocity gradient should be, and then try to estimate this term. Okay. And then once you estimate the rate of heat generation, you should be able to solve all these other problems, and you can translate that into rate of gravitational energy. Because they say you want to do it until your water's until you're boiling yourself. So you know how long that'll take, because you know how much energy you need, and you should be able to solve for this. So for all these equations, basically, dE dt is just going to be like energy divided by time. We're not going to do any calculus. This is just like we call this scaling. Okay, where derivatives just become ratios, and we're basically this is going to be like mu du tu dy, where this would be y. Okay, and u would be the velocity of your hand, for example, equals hand velocity, which is I don't know how fast you can move your hand, but it's going to be like less than a meter per second probably. Okay, we have the homework solutions are on you. I think it's your responsibility to try to find me, preferably not before Tuesday at 10 p.m. before the quiz. Like preferably, like, you know, where I can actually have time to respond. Like if you are totally lost with the index notation, please try to catch up, because I don't want to. I mean, half the class is perfect on this homework, so we're not going to be doing a makeup quiz. Like that quiz is what your grade is going to be. So please, you got 5 days next week. 2 days, I'll be here today, tomorrow, and Friday, and Monday and Tuesday. Like, look at those, come with some like concise questions, and either ask your group, but I want us to be at least as much on the same page as possible by the quiz day next week. And I will give you identities. You shouldn't have to memorize anything, but you should know like how to do stuff. Anything that you need me to write on the board, I'll write on the board for the quiz. But you have to be able to derive things on your own.